Ninth lecture, and the topic of today's lecture is rectifiers and power supplies. We are going to study some practical circuits in which diodes are utilized, and in our analysis of the circuits we shall assume that the diodes are ideal. That means diodes behave as switches. When they are on, the voltage drop across them is 0 and the current is limited only by the external circuit. There is no other limitation. This is what we are going to assume. The simplest rectifier circuit is the so-called half-wave rectifier, which uses only one diode, and the circuit is like this. The AC is applied between the two input points and then is connected to a load RL. The output voltage is taken from here, and there is an AC source here. Now the AC source you could connect to the DC main, the AC mains. The AC mains will give you 230 volt, and therefore the voltage that you can get across RL shall be fixed. It will be the rectified 230 volt and its average value. In practice, however, we require varying voltages. For example, for operating an op-amp, we require plus 12 and minus 12. For operating a typical digital logic circuit, perhaps we require 5 volt. For some other application, we might require 18 volt. For operating a high voltage transmitter tube, we may require a kilovolt of DC, and therefore the DC level, the DC voltage that is developed is controlled by a device known as a transformer. The transformer at the input circuit, this is the main supply, 230 volt, 50 hertz. The purpose of the transformer is to step up or step down the AC voltage in such a manner that the appropriate DC voltage is developed across RL. So we shall call this simply V, the voltage across the transformer secondary, and it is this voltage V is a sinusoidal voltage Vm sin omega t. The turns ratio of the transformer shall determine what V shall be. Obviously V can be positive as well as negative, and if we do this polarity, then when V is positive, V has this polarity, the diode conducts. When V has the opposite polarity, that is for the negative half cycle, the diode does not conduct, and therefore the current in the circuit the current in the circuit, let's say I, shall be half sinusoids. The I shall only reflect the positive halves of V. In other words, if you draw a sketch of I versus t, omega t, then what you shall get is only these half sinusoids, 0 to pi, then pi to 2 pi it shall be 0, and then 2 pi to 3 pi it shall again be a half cycle, and so on and so forth. Alright, this will be the current waveform, and the voltage across the load is simply current multiplied by resistance, and therefore the voltage waveform shall also have the same magnitude, the same type of waveform, not magnitude, okay, same type of waveform, current multiplied by RL. Now in analyzing this circuit we assume that the transformer is ideal. In other words, the transformer has no internal resistance, no losses, so that effectively if we look at the transformer back, it behaves like an ideal voltage source. This is one assumption, and the second assumption is that the diode is ideal, that is, it behaves like an ideal switch. Therefore the equivalent circuit of the rectifier is that we apply V, which is equal to Vm sin omega t, replace the transformer by an ideal voltage source. In practice it is not so. The transformer has losses, and therefore there shall be some drop there shall be an internal resistance small r here, which we are ignoring, and then we have the load RL. The the waveform, as I told you, is like this. This is omega t equal to theta, let us say, and we plot current as well as voltage. If the voltage waveform is like this, sinusoid, this is V, then the current waveform, the current flows only in during positive halves, and therefore the current waveforms are like this. These are the current waveforms, and the values of omega t are 0, pi, 2 pi, 3 pi, and so on. And you notice that during the positive half cycles, that is I of t is equal to Vm sine omega t divided by RL. This holds for omega t between 0 and pi, that is 0 less than equal to omega t less than equal to pi, whereas the current is 0 for pi less than equal to omega t less than equal to 2 pi. One cycle is good enough to find out average and other values. This is the current waveform. Okay, if this is the current waveform, then obviously its DC value or the average value can be found out very simply. Let me draw the waveform again. It is this is 0, pi, 2 pi. Our consideration can be limited to one period. This is I and this is omega t equal to theta. Notice we are not working in terms of t, we are multiplying, we are making omega t as the new variable, because this helps us in doing the algebra and the integration and so on. I dc, the average value of this current, obviously is 1 over 2 pi, the average is to be over one period, 1 over 2 pi integral, the current exists only over this interval 0 to pi, and therefore we integrate between 0 and pi, and then Vm sine of theta divided by RL. This is the average value of the current, and if you integrate this, it is very easy to show that this is simply Vm divided by pi RL. Pardon me? There has to be a d theta, of course, otherwise we cannot integrate. The value is Vm divided by pi RL, and you can see that Vm by RL, this quantity is simply the peak value of the current. This is Vm divided by RL, and if we call this I sub m, then the current is simply I sub m divided by pi. Alright, this is the average value, and the average value maybe it is somewhere here. Maybe this is IDC. Alright. Now you notice that the total waveform can be considered as DC, that is I of t can be considered as IDC plus an alternating component plus an AC component. Why AC? Because if you take out IDC, obviously the waveform can go positive as well as negative. In other words, if I plot this AC component versus theta, it will have simply this waveform, and so on. It can go positive as well as negative, and it is as if it is a ripple superimposed upon IDC, and it is called indeed the ripple component. This is a rather bad case of rectification. The value of the ripple is the difference between the maximum value of the current to the minimum value of the current, and so the value of the ripple here itself is Im. Alright, the value of the ripple is Im. Now we will see how to reduce the ripple later. Okay, I'll do that. My waveform of the current is like this. The green curve. This, as I said, can be written as an average component IDC plus a component which can go positive as well as negative. If I take out the average value from here, obviously if the average value is, the level is somewhere here. Suppose this is my IDC level. If I take this out, then obviously the current will be positive here, the AC component. I have not written this. AC component represents the green curve minus the black curve, and therefore it can go positive as well as negative. And the value of ripple, the ripple is defined as maximum value minus minimum value. Obviously the maximum value is Im and the minimum value is 0, and therefore the ripple is equal to Im. Alright, the ripple current is equal to Im. What we want is that the DC value, we want only the DC value, we don't want the ripple. So we want to get rid of the ripple, and we will see how to get rid of the ripple later. But first let us see if we can improve upon this situation. As I said, this is a very bad example of rectification, because, and also it is wasteful, because the negative half of the voltage is not utilized at all. The current is dumb or dead during the negative half of the cycle. So can we do something to utilize the negative half also? And that brings us to a circuit known as a full wave rectifier. Full wave rectifier can be of different construction. The one that uses 4 diodes in a bridge configuration is called a full wave bridge rectifier, and it is constructed like this. You had a Whetstone bridge kind of arrangement, and the input, let's say, is applied between this point and this point. The input AC is applied between these 2 points, V, small v equal to Vm sin omega t. And it is so arranged that during both halves of small v, current flows in the load in the same direction, and this is achieved like this. You have a diode here, then the load is connected between the other diagonal of the bridge. This is the load RL, and another diode is connected like this. So when V has this polarity, the current flows like this. Current flows like this, then through RL and then through this. Alright. On the other hand, when V polarity goes reverse, that is the lower end becomes positive with respect to the upper end, while current flows like this. There is another diode connected here, and a diode connected here. Alright. So what happens when this becomes positive and this becomes negative? Current flows like this through this diode, then through this load in the same direction as in the previous case, then through this diode, and finally to the source. Is this point clear?
We could have used only 2 diodes instead of 4 diodes.
Yeah, we'll come to this a little later. Yes, we could have used 2 diodes only. We'll come to that circuit a little later. But this is a very popular circuit, a bridge rectifier, particularly for instrumentation applications. Well, how does one supply the AC? Depending on what voltage, what DC voltage you want, you should use a transformer to step up or step down, and therefore what we have is, we have a transformer here, these parallel lines stand for the core of the transformer. Usually these are iron cored transformers, and this is symbolically represented by these vertical lines. So there is a transformer here. I have shown this as a step down. This is the main supply that is 230 volt and 50 hertz. All right. This is transformed into V, which is Vm sin omega t, and in both halves the current flows in the same direction through RL, and therefore if my voltage waveform is like this, then the current waveform, current shall be determined by, if the diodes are ideal, then the current shall be determined only by RL. All right. So Vm sin omega t by RL, and it will flow like this. During the negative half also current flows in the same direction, and therefore it is as if the negative half is flipped into the positive half, and the current flows like this. And therefore both halves of the sinusoid are utilized, and this is why it is called a full wave rectifier. Both halves of the sine wave are utilized, and it's called a full wave rectifier. Because the diodes are in a bridge configuration, it is called a full wave bridge rectifier. And obviously now, well, let me label them. This is the V and this is I. Obviously now, as far as I is concerned, the DC value, the average value, shall be twice the value for the half wave rectifier, and without any calculation I can say that I DC shall be equal to twice Im peak value divided by pi, where Im is Vm divided by RL. All right, is this point clear? As compared to the half wave rectifier, because both halves are utilized and they are identical in area, and therefore the area under the curve is simply twice the previous area, and therefore the DC value or the average value becomes twice the previous value, twice Im by pi. One of the disadvantages of this circuit is that it uses 4 diodes, and that during each half of the waveform the load is in series with 2 diodes, 1, 2, similarly 1 and 2, and therefore if the diodes are non-ideal, then twice the drop across one diode shall occur during each half of current flow, and therefore the internal resistance of the DC supply between these 2 points, this is the polarity, will be higher than in the half wave rectifier. That occurs only when the diodes are non-ideal, and all practical diodes are non-ideal, and therefore this is a disadvantage. But the advantage of this circuit as compared to the one that we are going to discuss now, using only 2 diodes, is that the transformer becomes inexpensive. Why? Because in the alternative circuit for a full wave rectifier, using only 2 diodes instead of 4 in a bridge requires a transformer which is to be center tapped. That is, I require a transformer like this. Okay, first let me draw the rectifier circuit, then I shall draw the transformer. We have the load is here, and this is one of the diodes, call this D1, and the other diode is here. All right, the circuit is like this. You have a transformer here and the load is connected to the center point of the transformer, which usually is connected to ground, but it is not necessary that it is. Usually this point is connected to ground, and the primary of the transformer is the usual circuit, 230 volt 50 hertz. It is either stepped up or stepped down by means of this transformer, center tap transformer. So the two halves are identical. In other words, if I call this voltage as V1 and this voltage as V2, I should have the opposite polarity. Then V1 and V2, except for polarity, they are identical. All right. So let's say V1 equal to Vm sin omega t, then V2 is simply the opposite of Vm, phase difference of 180 degrees. We have taken this polarity to indicate that when the transformer is such that the secondary voltage from here to here has higher potential here compared to the lower point, then it is this diode D1 which conducts. That is, when the transformer, when the excitation is such that this point is positive with respect to the lower point, then V1 is positive and V2 is negative. Is that clear? You are measuring the voltage between this point and this point. This is what is transformed. For example, if this is a 1:2 transformer, then 230 volt here will lead to 460 volts here, with this polarity positive and this negative. Now the total voltage from here to here is V1 plus V1 minus V2, because I have taken the opposite polarity. You need not bother about the polarity now, but the only thing you have to consider is when this point is positive with respect to this point, then this is positive with respect to this point, center tap, and the center tap is positive with respect to the lowest point, and therefore it is only D1 which can conduct, D2 cannot conduct. When D1 conducts, the current flows like this through RL, it goes back to the transformer center tap. On the other hand, when the transformer changes its polarity, secondary voltage changes its polarity, V2 becomes positive, that is, this point becomes positive with respect to ground. So D1 cannot conduct, it is D2 which conducts. In both cases, the current flows through RL in the same direction, and therefore the two diodes here achieve the same purpose as 4 diodes in the bridge rectifier circuit, except for the fact that it requires a costly transformer. The cost of a diode is much less than the cost of a transformer, and the total cost of this circuit is much higher than the cost of the bridge rectifier circuit, and therefore the bridge rectifier circuit is very popular in non-critical applications, non-critical where the diode non-idealness is not of great concern, does not affect your performance very badly. All right. So the bridge rectifier is favored, whereas this will be favored in critical applications where you will be prepared to spend the money required for a center tapped transformer. You notice that IDC, if the diodes are ideal, IDC is the same as in the previous case, namely twice Im divided by pi, where Im is equal to Vm divided by RL. What is this Vm? It is the peak value of either half, either V1 or V2. Is that clear? Whereas in the previous case, Vm was the total voltage, Vm was the peak value of the total voltage developed across this. So does it mean that this develops a lower voltage as compared to the two diode rectifier? Yes? If this Vm and this Vm are identical, then obviously the 2 diode rectifier develops a higher voltage, and this is where you pay the price. Effectively, it is the peak value of the voltage developed across half of the transformer, and more the number of turns, the more you pay, because you use more copper wire, and you use more core, more iron, and you have to pay for the metal. All right. So this is an expensive proposition, but in critical applications this is what shall be preferred. For example, in the laboratory power supply that you see, I defined a power supply last time. What is a power supply? It's a rectifier in combination with a filter. A filter gets rid of the ripple component, AC component. All right. In the full wave rectifier, if this is the waveform of the current and the average is, let's say, somewhere here, then you see I of t is equal to I dc plus an AC component, and the AC component has the same waveform as this violet curve, except that this black then represents the 0 level. All right, the black represents the 0 level. The question now arises, how do we improve the situation? How do we get rid of the ripple? This is also a bad case of a ripple, and therefore what we do is we apply a filter. There are various kinds of filters that can be used, and as I told you earlier, filters will use either an inductor or capacitor or both. All right. The idea is that if you have a current, let's say consider a current generator, this supplies a load, and this current consists of DC as well as AC. If somehow we do not allow the AC component to pass through the resistance, then obviously we shall do our job. That is, if we provide, the basic idea is this, basic concept, if we provide across the load a 2-terminal component which allows only AC to pass but not DC, obviously that component has to be a capacitor. So as far as AC current is concerned, AC component passes through the capacitor. It is the DC which passes through the resistor, and therefore as far as AC is concerned, the capacitor provides an easy path, so most of the AC flows through the capacitor, nothing goes to the DC, to the load. All right. This is what basically filtering is. Or the alternative way of looking at this is that we have a VDC plus VAC, a voltage source, and then what I do is it's connected to the load RL. Well, I don't allow the AC component to go to RL, to drop across RL. What I do is I use an inductor here. Inductor, as you know, drops the AC component. As far as DC is concerned, the inductor is a short, isn't that right? Inductor, the voltage across the inductor is L di dt. So as far as DC component is concerned, d dt of IDC is equal to 0, and therefore an inductor does not drop DC. So the DC shall be dropped across RL, and it's the AC which shall be dropped in the inductor. A better structure would be you use an inductor as well as a capacitor. All right. Accordingly, this is called a capacitor filter. If you have a single inductor, it's called an inductor filter. If you have a situation like this, an inductor and a capacitor, it is called an L filter. It looks like the letter L looked from your side, okay. This is called an L filter. Or you could have an inductor, then a capacitor, and again an inductor, then the load. This obviously looks like the English letter T, and therefore this is called a T filter. you could have a variation of this is you have a capacitor here first to start with, then you have an inductor, then you have a capacitor, and then the load. This obviously looks like the Greek letter pi, and therefore it is called a pi filter. There are various kinds of filters possible: capacitor filter, inductor filter, L filter, T filter, and pi filter, and all of them use inductors and resistors. The basic idea is inductors and capacitors. The basic idea is well, you notice that in all these circuits, whenever you use a capacitor, the capacitor is in shunt. Capacitor provides a shunt path. It shunts out the current, whereas an inductor is in the series path, so it drops the AC voltage. AC voltage is not allowed to go to the load by means of the inductor, which is therefore to be put in series, whereas capacitor provides an easy path for the alternating component of current, and therefore it is provided in shunt, so that before the current can have an opportunity to reach the load, it is shunted out. All right, is that clear? We consider at this point in the course only the simplest filter, namely, let us consider a half wave rectifier and a capacitor filter. Capacitor C, then this is RL, and let us say we replace the transformer by means of a ideal voltage source, which is Vm sin omega t. Then you know that without the capacitor, the waveform of the current let us look at the voltage. Waveform of V first. Waveform of V is like this. Okay, now let us see how does the current flow. To start with, let me use a different color. To start with, you see, when small v is positive and negative like this, when its polarities are like this, what happens? The diode passes current. This current charges the capacitor. All right, this current, the current passing through the diode, it charges the capacitor. All right, there is a current through RL also, we will come to that, but it charges the capacitor, and therefore the capacitor voltage, if you call this voltage as V sub C is the same as the voltage across the load, because the two components are in parallel. V sub C is the same as VL. What happens to V sub C? It rises, it accumulates charge. And how long can it accumulate charge? Well, it goes on accumulating charge till it reaches the peak value. At this point, this voltage itself decreases, and the capacitor cannot change its voltage instantaneously, and therefore the capacitor holds at the maximum value, let us say Vm. The capacitor holds at the maximum value Vm. This voltage diminishes below Vm, and therefore the diode ceases to conduct. Is that clear? No. All right. When V, small v, is rising like this, this is the waveform for V. When small v rises, the diode conducts, the diode drops nothing, the diode is ideal, and therefore the total voltage Vm sin omega t appears across Vc. And what happens when this voltage rises, the capacitor also charges. Capacitor charges to what voltage? It charges up to V equal to Vm. Now what happens? Small v now decreases below Vm. The capacitor cannot change its charge, and therefore it remains at Vm, whereas this voltage decreases below Vm, so the diode now becomes reverse biased. The diode conducts only when the anode is positive with respect to the cathode. Now the cathode has become positive with respect to anode, therefore the diode ceases to conduct. What happens to the capacitor then? Capacitor becomes disconnected from the supply, and but it finds a path through RL. So it supplies a current to RL, all right, and the capacitor voltage gradually decreases. It decreases in an exponential manner, and therefore the capacitor voltage starts decreasing like this till, well, during the whole of this period, during the whole of this interval, the diode remains inactive. The diode does not operate. It remains open. As soon as the capacitor voltage reaches this point, now it finds that indeed the anode of the diode, the voltage at the anode of the diode is now increasing, and therefore the capacitor which had lost some charge now begins acquiring charge again, all right, up to the maximum, all right. Then once again the diode ceases to conduct, and therefore the capacitor once again starts diminishing like this. This is the waveform of V sub C, the voltage across the capacitor, which is the same as the voltage across the load VL. And you notice that when the capacitor was not there, the voltage waveform would simply consist of the positive half of this, then the positive half of this, and then the positive half of the next cycle, and so on. Now what is happening is this large gap, this negative half which was left completely unutilized, the capacitor now, because of its property of storing charge, it fills out some of the void. What we would have liked is, if it had remained constant like this, then obviously we would have gotten absolutely constant value of DC. Unfortunately that does not happen because there is a load, and as soon as the diode starts being open or non-conducting, as soon as the diode becomes non-conducting, the capacitor loses charge through RL. The charge decays exponentially till the diode gets an opportunity to conduct again, and this repeats. And therefore if you observe, if you connect an oscilloscope across the load, what you shall observe is this: an exponentially decaying wave, then a little rise, then again exponentially decaying, little rise, again exponential, and so on. This is what we shall repeat. Isn't it obvious that the area under the voltage curve, under the capacitor voltage or the load voltage curve, has now increased, and therefore the DC value has increased? Is that okay? This is one way of rectifying the situation in a half wave rectifier. Not only that, if the DC value has increased, what is the other phenomenon that accompanies this? The ripple voltage, that is the maximum fluctuation between maximum and minimum, has decreased, and therefore this is what the filter does. One way of looking at the filter, at the capacitor, is a very simplistic way, that the alternating component of the current is provided an easy path. Another way, another more illuminating way, is to look at the charging and discharging of the capacitor. Now let us go a little deeper into this phenomenon and see what happens to the diode current. Okay, obviously the diode does not conduct during this decaying part. It starts conducting here, all right, and as you know, the diode current is limited only by, when the diode conducts, the diode current is limited only by the external load, and therefore what happens is the diode starts conducting here. Let me use a different color. The diode starts conducting here. Suddenly the diode current rises, and when does the diode stop conducting? At this point. And therefore what happens is the diode current flows like this. It flows in a pulse during a part of the half wave. If the capacitor was not there, the diode current was flowing throughout the positive half cycle. The diode current was flowing like this. Now the diode current flows only for a small interval of time. Let's call this as T2 and this as T1. It is during T2 and T1, it is during T2 minus T1 that the diode current flows. In every subsequent positive half cycle, this is what happens. The diode current flows in pulses. You can see this also on the oscilloscope. If you take the current waveform, how do you observe the current waveform? How do you observe a current waveform in an oscilloscope? You allow the current to drop in a resistance. So you use a small resistance here, maybe 10 ohms. This will of course affect the performance of the circuit badly. It will deteriorate the performance of the circuit, but you can at least see, if you use a small resistance here and connect the oscilloscope terminals across this, then you can see the diode waveform and you will see that it flows in pulses like this. This would be the shape that one can observe on the oscilloscope. Alright, that the diode current flows for a short interval. Now can you tell me if T2 minus T1 becomes shorter and shorter?
There is no power loss in the diode.
That's right, the power loss in the diode decreases. Not only that, there is something else that happens to the DC voltage that is developed. If T2 minus T1 was 0, then the VDC would have been constant, and therefore the shorter the interval of diode conduction, the better would be the rectification, or the less will be the ripple voltage. Now if I draw this waveform again, let's say I start from, forget about the initial part. Initially for the first half cycle, the capacitor charges. Then except for this part, the phenomenon is repetitive. So forget about that. What I have is, from here, let's say this voltage is Vm. From here there is an exponential decay. Should use a different color. There is an exponential decay, then it rises, the capacitor charges, then there is an exponential decay like this, and so on. Alright, what I said was that this was T1 and this was T2. If T2 minus T1, before that, can you tell me what will be the equation to this decay? Exponential, so it would be Vm, it starts decaying from Vm, e to the power minus T minus T2, it starts from T2, divided by RC. Okay, this is the equation to this curve. Alright, so it exponentially decays. Now if T1 minus T2 is small, then what is the difference between T3 and T1? T3 minus T1 should be equal to 1 complete period, isn't that right? So T3 minus T1 should be equal to capital T, the time period of the wave. This happens exactly the same point in the next cycle, and so on and so forth.
So why do you get in the decay of the voltage that is due to the capacitor?
Yes.
Across the capacitor, why do you get T1 minus T2?
T minus T2. At T equal to T2, the value is Vm, and then it decays. Similarly, you could write for this part. You have to have prime somewhere, okay, the initial value of the time. But do you understand this point, that the difference between T3 and T1 is exactly equal to 1 time period? Alright, is that clear?
So can you explain that again?
Can I explain that again? You see, between T3, that is the point at which it starts charging again, and the point it had started charging earlier, the difference is exactly 1 time period. Alright, from here to here it is 1 time period. We have advanced it by T1 here. This is also advanced by T1. and therefore it's exactly one time period. It is important to understand that this is one time period. During this time period, how much charge has been transferred to the load? Obviously IDC times capital T. During one time period, the total charge transferred from the capacitor to the load, and this is replenished during T1 to T2. Isn't that right? This charge, the charge that the capacitor loses to the load, right, it's a beautiful physical equality, conservation of charge. The charge that the capacitor loses, it is that amount of charge, only that amount of charge that the capacitor gains during the time that the diode conducts. Alright. So if this difference is VR, then what is VR? VR is obviously the difference between the maximum value and the minimum value of the voltage across the load, and therefore VR is the, by definition, the ripple voltage. Alright, this is the ripple voltage. And if a capacitor charges through a voltage VR, how much charge does it acquire? C times VR, and therefore these two should be equal. Is this clear? The capacitor loses charge during this period, alright, and the charge lost is equal to IDC multiplied by capital T. I have made an assumption here which you did not object to.
So that the capacitor gets charged in 0 time.
No, that is not the case.
Cycle, cycle, no current flows to the load.
No, even not that.
Linear capacitor.
Capacitor charges only between T3 and T2. Capacitor discharges only between T3 and T2. Whereas I multiplied IDC by capital T. T3 minus T2 is not capital T. T3 minus T1 is capital T.
But T1 and T2 are assumed
That is the assumption. What I am assuming is that the diode current flows for a very short time. That is T2 minus T1 is very small. Therefore, I should use an approximation sign here. This is approximately equal. Let me repeat. The charge lost by the capacitor during one period is IDC multiplied by T, and the charge gained by the capacitor, it can gain only when the diode current flows. Therefore, it gains during the time interval T1 to T2, and that charge is C times VR if VR is the ripple voltage, and therefore the required value of C to obtain a required ripple level, obviously the ripple level will depend on C. Suppose RC product is very large, then obviously the decay will be very small. So T2 minus T1 would be small. Is that clear? If the RC product is very large, then the decay would be small. It will fall very slowly, and therefore T2 minus T1 will be still smaller, and the ripple voltage will be smaller. So it is the value of capacitance C which controls the ripple voltage. And to get a certain ripple voltage VR, the relationship is that IDCT shall be equal to CVR approximately, and therefore the required value of C is given by IDC capital T divided by VR. All right. Now what is IDC? It is VDC divided by RL. And what is capital T in terms of frequency?
2 pi by
1 by F. Capital T is 1 by F. F is in hertz. No, omega. Omega is 2 pi F, and F is 1 over T. F is the frequency in cycles per second or in hertz. So it becomes RLF, then VDC by VR. All right. Is that clear? VDC by VR. Now suppose I want, suppose my RL is 1K. What is F? F is 50 hertz, 50 hertz. And suppose I want a 1% ripple. What does 1% ripple mean? 1%, VR is 1% of VDC. Therefore, what would be VDC divided by VR? 100. No. VDC by VR. VR by VDC is 0.01. If it is 1% ripple, 1% ripple, all right. Therefore, I can calculate my C, it would be 100 divided by 1K is 1000 multiplied by 50. So many farads. It would be a large capacitor, whatever the value is. It will be in the order of hundreds of microfarads, okay. But this is the type of capacitor that has to be used. Now, if VDC is specified, then you can calculate the turns ratio required for the transformer. Suppose VDC is specified as 10 volt, then VDC is approximately equal to what?
10 volt is what?
VDC. The DC voltage required across the capacitor of the load is 10 volt. Then VDC is approximately equal to VM, the peak voltage across the secondary. And therefore, the transformation ratio that you need is 230 is to 10. Is that correct?
So should VDC be equal to VM only?
VDC is approximately equal to VM. Because when I say,
0.6 DM.
So please explain.
Okay. You see, VDC, ideally, if the capacitor was infinitely large, if RC product was very large, then the ripple voltage would have been very small, and therefore the capacitor would have discharged very slowly, and therefore the voltage, the DC voltage, would have been approximately equal to VM, the peak value. In any case, in this example, we have specified that the ripple voltage is only 1%, and therefore the voltage across the load can deviate from VM by only 0.01. Can it increase by 0.01? No, it's decreased because the capacitor decays, and therefore VDC is approximately equal to VM. Now, beware of the trap. What I am saying is, if this is so, then my turns ratio of the transformer, because I am feeding the transformer.
Say it will be the opposite. Say it will be 10 is to 230.
No, I have to step down, and therefore the primary must have a larger number of turns. But I still have made a mistake, which has not been detected. 10 is the peak value of the secondary. 230 is RMS, so I must multiply it by √2. This would be the turns ratio. Is that clear? And the total rectifier design is complete. All that you need is the transformer. You have specified the turns ratio. Go to the market and buy the costliest transformer. The costlier it is, the better is the quality. You buy a cheap transformer and you make your life miserable. And you buy a capacitor. The capacitor also, there are various qualities of capacitor. Hundreds of microfarad of capacitor, 500 microfarad, is available only in electrolyte. It is an electrolytic capacitor, and there are differences between Bell capacitors and other company capacitors. There are good companies, bad companies, and so on, and you should buy the best that is available. And you can go to the lab and wear up the circuit. I guess you have an experiment to do with a half-wave rectifier in the laboratory, and you can observe all these waveforms and the phenomena in the laboratory. On the next occasion, that is Monday, we shall take up some wave shaping circuits.